Yes. Hey, Chris, do you wanna? Oh, you're gonna eat later, you guys, or the pizza's gonna get cold. Yeah, yeah. There's some plates over there on the top. Uh, we're having a pizza break and also a shirt break, folks. But yeah, sequence. All right, so let's see. So this is from Belding, Mitchell's Foundations of Analysis, Lemma 141. We've done this before, so this will be a good review, but it will be, and maybe this is the one that we'll do the reflection business on, is bounded. All right, take this and stick it right here. So Liliana, you can do like an hour today. As soon as this lemma is done, you can skip, okay?
Okay.
Yeah, okay, yeah. So as soon as this is done, you can, yeah, take off or stay on if you want, and then I'll send you the assignment around 4, 5, or tonight. And it's going to be like, max like a page for that. Okay, I can't eat that stuff. I'll try to eat apparently the crust is what's so favored. And I brought you guys for those who love the papers. Okay. All right, so we have the lemma 4.414. Every convergence sequence is bounded. So just like in a poem, if you have the metaphor tree, you're going to end up with branches, you're going to end up with leaves, you're going to end up with grains on the trunk that tells you the age of the thing, right? You will also, so there's a limit to how long a tree can last. A convergence sequence also has a limit where it goes and dies somewhere around a limit. And then, so if you see the tree, you have leaves, branches, trunk, you have spring. Spring comes in because if it's a seasonal, the leaves come back in spring. In winter, the leaves fall. If you see the term here, so it's this lecture today is taking another turn. The poetic turn here. What's the what should I write below it? What are the things that this phrase here? Oh, and remember, every is an important term. So that convergence sequence, we need what? We need an n. Okay, so that means all the terms that come after the threshold term, all the terms an that come after the threshold term. So, and I'll write that down. So what this is saying to us is all terms a small n. Oh, this is my, sorry, I need to use my red pen here. All terms an, or and actually this should be in red too, since this is my commentary. All terms an after the threshold term a uppercase n, and all these terms are the clustering terms. And they're clustering around the limit. So if this is the case, then, and we're going to skip if and then we have this situation. Terms an and their distance from the limit a is always less than some positive number epsilon. Okay. So we've just unpacked this, and it turns out, since this is a direct proof, we're going to lay all of this out. And in our case, we'll also draw the picture. That will be the stuff we will be using to prove to prove that a convergence sequence is bounded. In other words, we will use all of this to generate a upper bound for this sequence using the triangle inequality and also sets. Okay, so bounded means it is, so this is a box. Also, there's another thing that we can say. This is the commentary that I will, let's say, this is the limit. This is the clustering terms. And this is a positive number. And I'm going to now, if you've taken the notes already, I'm going to delete this. The idea is you should be able to read it. In other words, the idea here is as soon as you see this phrase, convergence sequence, this should pop in your head. Okay. That is the whole idea. Because when this pops up in your head, this is what you're going to use to prove the sequence, not this phrase, because there's English, but there are sentences, but the math is going on. Now, another way to think about, another thing that pops out in this metaphor is limit of the sequence. Here, these are clustering terms. Here, the AN is all of the sequence. When n goes to infinity equals this. So let's do this. This is clustering terms. Clustering terms around the limit A. This is the all the terms in the sequence. So it's a huge difference between those two. So when you're writing the proof and you put this, you're saying something about the whole sequence. When you put this part with this condition, n is greater than n, uppercase n, you're saying we're discussing the clustering terms around A when it has congealed. Okay, so I'm going to, so remember this is all the terms in the sequence, the whole sequence. This is just the terms that, and then I'm going to. That AN is only all terms where it has it. No, so this is, sorry. So this is only clustering terms because of this condition. Okay. The limit here doesn't have this condition, therefore, we're talking about the whole. Okay, so in other words, that's a very good question. So the question is, is this all the terms in the sequence, the whole sequence, because there's a limit? No, because this condition is not there. N is greater than uppercase N. If the condition was there, then we would be looking for the limit in the clustering term, which is where it lies. This is saying the whole sequence has a limit. This is saying we are concerned about the distances between the clustering terms and the limit. Yes.
I was going to say, since there's no condition in the actual, was it the set at the bottom, or?
No, the convergence sequence says this. Yeah. And it also says this. There are two ways to restate and they're equivalent. When you, okay, so in the case of sequences, when you expand this, you get, when you shrink this or this, you get this. So in other words, convergence sequence has a limit. The definition of the limit is this. So actually, let's write. That's a very good question. What's going on here is, let's put some arrows here. Convergence sequence has a limit. the definition of a limit of a sequence is this. Okay, because this looks very much like the definition of a limit of a function. But in fact, this is a sequence. And when you expand it, the expansion of this, if this was a function, let's do this. I did that with just for the sake of it. If I did this, so I'm going to put x goes to, we do x. Okay, let's do x. And this goes to infinity. The function fx goes to L. That is saying that this function, which is not a sequence, something else entirely, when the values of x go to infinity, the function goes to this number L. Okay, this is compact, and when you expand it, you get what? Actually, I'm going to do A. Yeah, there we go. I'm forgetting my, but this becomes what? X, this is going to be delta, this is going to be greater than 0, or something like that. If this, then this thing here is the expanded version of the definition of a limit, right? So that's what's happened here as well. So you can write this or you can write this. Which thing is more useful? Obviously, this is in a proof. And then just double check if I got anything wrong, but basically that's, I think, probably not. Yeah. Yes. Ask me.
I don't know what question you asked.
Yes, you should. I can draw it and then it'll start to click.
Because I know the picture, the way you did it.
Yeah, so right here is the delta. Right here is A. That's the cluster point, and this is the limit. And then this is limit plus epsilon, limit minus epsilon. And then this guy here is A plus delta and A minus delta. And then these guys here are the x's. And here falls the f of x's. And the function goes like this. And hopefully, right, the x, as we shrink the delta, the x better fall here.
Okay, so these two terms, one just.
Yeah, we have to add another Greek alphabet because we're dealing with two x's. Here, we're only dealing with a set or just a real number line. Yeah, yeah. And so this gets moved over here because this is the crucial thing. This part is similar to this, identical. This is just something for us. Okay, all right, so that was a quick review. And we will be doing all this, and it's going to be horrendous. So the natural place to understand limits is, according to one of the textbooks, actually not these guys, but the other one, Bartle and Sherbert, is the sequences. Because you learn that there, and so their chapter on limits of sequences or sequences is before the function chapter. These guys don't care, so they have the function chapter first, and then the sequence. So we just skipped to chapter 4 here. Okay, why is it saying lemma 1? Yeah, it should be 4. Yeah, I just caught this. That would have killed my But we fixed it inside the video. All right, now what about bounded? I know you guys remember this. Bounded means all terms an of the sequence, all terms an of the sequence are less than and not equal, just less than the upper bound m. That there is an upper bound.
We don't need to find like,
No, but if the set is not empty and there is an upper bound, then the set will have a least upper bound. That's one of the definitions, no, a theorem actually that we did do. I don't know when, but we did do it. Yeah. Okay, so everybody's clear what's going on here? Why is this all terms? Because there is, this condition is not there, n greater than n. When we prove this, when we get halfway, we think we'll be done. The problem is we are done for this condition, not for all the terms. And that's when the sets come in. No, the set comes in, we seem to have, yeah, actually the sets comes in to do that. Okay, so I'm gonna delete this. All right, so now we have, and this should have been in red, but it isn't, sorry. I'm not gonna fix this. This got unpacked into these two things, and bounded got unpacked to that. So in other words, we need to, what we have is this reality. Start eating. And this needs to be transformed into this. And to transform what we have on the left into that, or transform, or let's say use. We want to use, actually that's a better word, right? We want to use this to get here, okay? And to get there, we will have to also use things like triangle inequality. And we have to do triangle inequality property, and we have to do sets. Those two things will come in. And also the max function. We will also give epsilon a new value so that we can control, so that we can construct the what is it? Whatever it is. Okay, all right, let's start doing the proof. Okay, let's delete all this. And what we're gonna do is we're gonna leave the top line on, and I'm gonna, as soon as I've used this, I'm gonna delete that. So the proof goes, okay, so the proof goes, suppose that, and so today we're gonna figure out why this, in this lemma, this first line happens. Because limit as n goes to infinity of the sequence, all terms of the sequence an, this, as n goes to infinity, the sequence ends up on this number here, a, the limit. So sequence has a limit. Where did we, so we just generated the first line. So let's call this L1. So that's our first line of our proof. And where did we get it from? So this is our notes here. How were we able to create the first line? Yes. Yes, very good. Definition. Okay, very good answer. Convergent sequence. And just like in my poetry class, I will ask you, give me another word for suppose. Very good. Very good. We have assumed, and let's put that word up here, or let me put it here in this block here. These are our, this is our anti, this is not working out. This is the antecedent, and this is our consequent. And this is to prove or show. Okay, so we are what do we do? We assume this to be true. Assume the antecedent to be true and start generating the proof, because this is a direct proof. Direct, actually, in fact, all proofs are direct proofs. Even the proof by contradiction. Yeah, okay. I think, though I could be wrong. So now it says line 2, we need to modify. So this is where the intuition of the mathematician comes in, which we still don't have. Is that if we set this to 1, we will be able to, using the triangle inequality, since I've read the proof and we've all seen it, that will allow us, if we add 1 to the value of the limit, that gets us out of and to the right of the clustering terms within the epsilon distance. So if epsilon distance is 1, because it can be anything, it's up to us. So if we do that, it will all work out. So epsilon taking, the book goes, taking epsilon to be 1. If you took epsilon to be 100, it will become nonsensical. So 1 is fine, is legit. Okay. If we do that, then we can say, and now we're going to say this, there exists. So how were we able to, where did the epsilon come from? Definition of the convergence sequence. We have assumed this to be true. We can use that and give it a value. Now I'm going to write some more lines. That's the whole thing today, is where are these lines being generated from? They're generated from our, we are assuming the antecedent to be true. So yes.
So they come from the definition of what we use.
Yes, that is the, because these two words have their definition. Definitions, we're applying the definitions because the definitions have been assumed to be true. And so here's the other thing. Let's say we assume this to be a convergence sequence. We're using all of this, and we are unable to show that a convergence sequence is bounded. That means not that the definition was wrong, but that convergence sequences are not bounded. If we assume them to be true and we are able to get there, then this theorem is true. Okay, all right. So exists, what exists? We're gonna go with n. And then he says there is a number n such that if, where is he going to go? He's going straight to the definition right there. If, so we just copy and paste here, n is greater than n, then this is our shorthand version. I'm adding the words if and then. A and all the clustering terms minus a, which is the distance between all the clustering terms and the limit a, will always be smaller than or epsilon. All the terms will fall within the epsilon distance of the limit. All, this is a gloss on this thing, should be read. All the clustering terms a small n will fall within the epsilon distance of the limit a. Okay, so what is wrong with line 2? Epsilon is 1. Yeah, I haven't used it. So this is our epsilon. So what we've done is we have modified that. We've taken the liberty to modify one of the conditions that are assumed to be true. And that is fine, because epsilon is any number. We give it a specific number, and that seems to, a lot of the proofs are done like that. Should we draw it out? Why not? So we're gonna say pick. Now I'm coming up with my notationals. Pick one. Pick one looks like, should we do it in red? I'll do it in blue. So here we go. Pick one, which is not in the textbook. Real number line. We have A1, A2, A3, and then we hit a uppercase N, the threshold point, threshold term, it's the same thing. And then I'm going to put in, this is A right here. After it hits the threshold points, all the ANs fall within the epsilon distance. Okay, so yes, and I made yet another mistake again. And I don't know, I mean, I think we could just write epsilon, but we'll forget.
Yeah.
So we need to have this here. Okay, so everything after the threshold term, and we're keeping the threshold term out of the gathering storm around our holy god A, is because this guy here, n is greater, not equal to. It depends on the textbook. And I think this is a clean way to do this, which Belding and Mitchel are employing. Okay, all right, so then we are all set, we move on. And now the question is, can we do anything else?
Hey, quick question for you.
Oh, sorry, I'm like, holy shit, there's somebody back there in the room. Hey, Jake, sorry. That's just scared the hell out of me. Yes, Jake, finally.
California. What are you doing in this room, huh?
Yeah, okay, yes, sir.
Yeah. Hey, so
Yeah.
I'll try and let me see. So on like the section to the right of the sequence, like, so does that like the numbering, like, so like the, let's say it's like the 8th turn or 9th turn, does it go towards like the cluster or does it move away from the cluster?
Okay, so what's going on is that there might have been some terms here, and I'm not sure, but I've drawn it before like that, that this could be on the right-hand side of the clustering terms, there could have been A4, A5, and therefore N could be 6, and after that, all the AN terms would be the next term. Let's say if it's this one here, AN plus 1 would be 7. So there might be some stragglers out on the right-hand side, but mostly on the left-hand side. This set here, A1, A2, A3, and AN, and the terms to the right of the clustering terms, the right of this limit, outside of the clustering terms, those things are called these are the finitely many. So this is, we have finitely many here, and also finitely many. And here we have infinitely. Good thing you asked me, because I forgot to put this in many. Because this sequence is infinite. So once it hits the threshold term, it just goes here forever. This is happening forever. Terms are gathering forever within the within one distance of the limit A. This is happening forever. You can hear it ching, 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 like you're in Vegas.
So you could say like
Hmm.
A to the N is the last finite term, and then you can.
A uppercase N
Yeah.
is the last finite term. And the finite terms can be on both the right-hand side and the left-hand side, outside of the epsilon distance, which in our case is 1 from the limit. That is the holy gathering. Yeah, and the outsiders, that's us. We don't believe in A. Okay, now the question is, very good. Jake, did you understand that? Do you have another question? Or is California good?
Yeah. No, yeah, that makes sense.
Okay, California,
I think-
yes.
So
Mhm.
like the capital A, like that is like that's not
That
a
is a
number in the
Very good, very good. This is, California is really helping us here. A term in the sequence. Very important to remember that. The limit is a term in the sequence, folks, because otherwise you can't stick it inside the absolute value. Everything that goes in has to be the same. A generalized, each time that you run this, there's one specific term that you pick from the cluster and subtract it from this specific term A.
So, hey, I have one more question for you.
Yes, very good, very good. You're
Could
helping
you-
out. Mhm.
Yeah. Could you make a
Mhm.
graph of how this sequence would look? Because I haven't like once I see it, it'll click.
Okay, so what's happened is there's another proof where I actually create a sequence for myself to understand what was going on. For you, let me do something like this. So our sequence are A1, A2, A3. What he's trying to understand is A1 is actually A. So we've done that definition before. Definition of a sequence is a function. Sequence is a function that takes a natural number 1, 2, 3, uppercase N, lowercase n, m, and gives back a real number. So A1 actually represents, let's say 47 is cool. A2 is 53. A3 could be 33 if it's not strictly increasing. An, the n itself could be, let's say 5, but this thing could be 88. Okay?
Yeah.
And then there are more terms after that, right? That we're calling ANs. Maybe this one is 98. There's another AN that could be just 3. Sorry, I changed markers here. There could be the number 3 in here, number 4 in there, 225 million in there. Okay? So there's always, we have to keep, I keep forgetting this, that the index numbers are not the value of the sequence itself. The value of the sequence will look like real numbers with decimals and all kinds of things. Yes.
Yeah, okay, that makes sense.
Go ahead.
N of 3, or where 3, would that still be within epsilon?
Yes, yes. this a n, you could have a value of 3 in here. It doesn't matter because this is the real number generated by n. N could have been just 10. The 10th natural number generates 3. Okay. So always remember again the definition. The problem is that I shouldn't say that because we regard it as that I'm still confused. I think at this point in the book, we're dealing with not monotonic sequences, as in decreasing or increasing, just random. That's why I can stick these guys here without worrying. Because if it was just increasing, we would just go all the way up to, but not after A.
Yeah.
They increase to A.
Yeah,
And
I
then
think-
each of them would be in some kind of an order, depending on how you set it up. Like if AN is strictly the previous term previous term A sub n minus 1 is strictly less than the next term. Or actually, this is confusing. That's better. Computer science. So this means that every next number, because this is not index, this is actually a real number. And this is also a real number. So the real numbers are going to be arranged in increasing order. And A, if that's where they're going, will have to be quite big. So that's a different ball game. And so there's a lemma or a proof, a theorem that I'm not going to go in because I need to look at the book carefully. Are we dealing with increasing or not? But here we're not dealing with, because the topic of monotonic sequences are after this. And then there's a proof. So I'm very confident as we're doing this that the ANs are falling on both sides. And there might be some stragglers out here. So the terms of the sequence before and after the what is that? The absolute value definition. What should we call this thing? I don't know. The gathering. Let's just call it the gathering of clustering bastards. Okay, so all right. Does that answer? Who was I answering here?
I think it was big, but yeah, that makes sense. Okay,
all right.
I mean, I get it now. Is what I think.
Okay, all right,
like
very
you
good.
explaining it means like yeah.
Okay, and just remember, like if you forget, just ask me because this is tutorial style and it actually improves the video. It really does. Okay, because we did a quick review of the function, what the definition of the function is, which is a sequence, not function, but a sequence. Sequence is a function that takes a natural number and spits out a real number. Yeah.
I don't want to get sidetracked.
Yeah.
Big A
Yeah.
is not a term
It,
for
it is a term.
it is a term of A. So there is a value of n of little a.
Yes, yes, yeah. Oh, that's what you're saying. Oh, yeah, this guy here is A, and this n could be 15.
Okay.
Yeah, just like if this n here is 6, this n is 15, which means there will be only how many terms inside this?
Not
6, 9. You're only going to have 9 ANs inside before you hit A, and you're done, kind of. Oh, no, sorry, wrong. It's infinite.
Yeah, it's-
So infinite. So it will go on. After we hit A, the next term that falls into the gathering will be A16. There will be some real number. And then A17 and A18 and A infinite. On.
Oh, but it won't. Okay.
Right? One of the terms after AN will be the limit, because this is the term where the rest of them will always be A minus one dash distance or epsilon distance of the limit.
Okay.
Okay?
Okay.
It is, see, we've been doing this for a while and we're still like,
I didn't know
that's
that.
why this class is probably the hardest class you guys will take if you take the real analysis class. Because they're not, the professor is going to expect you to understand this on your own. They don't have the time, they have to cover the material. That's why in spring, this will be flipped. All this stuff will be, okay, all right, so is there anything else we can do? I think we have run into the limit of what we can do with our assumptions that we are holding true, the antecedent. And so it's time, because we want, what we want is, we've got this down. That means this can be used. Let me write this here. Used soon. And now we've come to an impasse, and that's where we go, oh, okay, we need to go there. So let's go. We have enough stuff. We'll be using this bit with 1 in it. We're gonna take this, modify that, and make it look like that, so that, no, use this to get here. Okay, we'll be using this to modify this thing to get there. So we haven't assumed, so this is not true yet, right? Not true yet. So this is also an interesting point I wanted to make. This whole thing is not, the inequality itself is not true yet. But which part of this thing is true? Or which part of that definition of the bounded, which is available to us? Is M available to us? No, because M we're going to be constructing. Is this part available? Because all it is saying it's a sequence of all the terms, right? So that is available. We have the sequence. So we can take this and go with it. Okay. So that's something that I was thinking about. That we are able to unpack this and use this to generate all of the stuff from the. How can we use that? It is available to us. In a very fundamental way, it is this part is true. True on its own, outside of the inequality. Okay, all right, so I'm gonna erase these guys, and I'm going to erase this. Okay. And our proof is gonna be, move this guy up. So we're in, of course, in the proof mode. And the book says, using triangle inequality. And I always like to add property. Prop. It's a prop. I like that. It's a prop. Property. And this property, this triangle inequality. So let's unpack it and give the definition just here. And the definition is going to be in red because it's a comment, not in the book. Less than and equal to that is the, okay. And the condition there, we're going to apply this thing to if, and that's when what I just said could have been completely wrong. So let's see if I was wrong completely. If n is greater than n. So I'm very sure, no, actually I'm still right. So it's true on its own, but we apply this condition on that guy. When we apply n greater than n, we are saying an now stands for all the terms that come after, not bigger, but after the threshold term. I think I have been using the wrong word, bigger. Yeah, I've been using after, so that's good. So we're going to apply this condition to this. So now we are here, we take this, because we really want to prove this, right? So this is an inequality. If you have an equation, for instance, so this is in a way, delete this here. Think of this as a something similar to a equation. This is left-hand side, and this is right-hand side. When somebody says, show x plus 1 equals 3, or let's say, I don't know, this doesn't look good, but let's do this. Okay, let's say that. You start here, and you go, okay, I want to get to this guy. So I'm going to take this, and I know that this is actually equal to x plus 1. And then this thing is actually equal to 3x, this whole thing. And oh, look, I have shown that the left-hand side equals this is terrible. This is like bogus and fake. But what I'm saying is you start with the left-hand side, make modifications and changes to it so that by the end of the page, you are on the right-hand side. So in other words, we need to prove that we take the left-hand side and then show that it is less than the right-hand side. But the right-hand side doesn't even exist. We have to create it. Okay, so, and we've already assumed that this is true. So, but when I put this condition on, now this guy is different. And I'm going to delete this line. I'm going to stick this right here. This is our modified definition that we'll be using. So this is line 2, this is line 3 of the proof. We still have the pick here. That's good. Okay, so this equals what? So we need to modify that so that we can get to something that looks like that. And yes, very good. And so we look at that because so at this point, we want to create this thing here, right? And then this, okay, so we're going to add and subtract because we already have an. And in this case, these are all the clustering terms only, not the whole thing. And then we want this to look like that because once we have something like this in our math here, we can replace that with this value. Right? So because this is the useful thing that we did when we modified the general definition and convergence sequence with our laying it out. So in this case, let me just, unfortunately, let's do it in this line here. We can then add and subtract. If you look at this, this resembles like that. And then, so this.
Okay.
Not yet. So,
Okay.
yeah. So now that we've done this, all we've done is added, subtracted A, because, why did we do this? Because we want this thing to appear here. Not this whole thing, but that part. Also, what else can we add and subtract? This is what we had, right? This is an assumption that we can bring in. We're bringing in one of our assumptions. So we laid it all out. The only change that's happened is that we brought in, we're going to be using triangle inequality, but the assumptions are still from the antecedent. Assumptions that we are using that we hold to be true are still from the antecedent. We have now officially started to make this happen, but the assumptions we are using are still from there. That allows us to add, not because we randomly, like I did that with you, I think. Can we use n? No, I think I did it with, what's his name? Thomas. No, n doesn't fit in because n is a natural number. Small n cannot go in here. Oh, this is already here. So we are left with that. No, that's the wrong way of reasoning it. what we want is we want something that looks like that so that we can remove it and use something that is reduced and simple. Just like in a math thing where at the end, you're going to a simplicity from complexity. Okay, so now that we've done this is just for the people on the internet. And then this guy, for those who won't be able to see it. Now we apply. We're going to apply triangle inequality to this line here. So this whole thing, according to the triangle inequality, is less than or equal to okay. And then this is right at the wrong place, but yeah. Well, we'll have to stick that in. Otherwise, I'll have to draw it again. So I'm going to do, we're going here, unfortunately. So the next step is to take this and replace it with that.
So it doesn't equal one, it's less than.
It's always less than one. This distance, every time we measure, that's the other thing I was trying to say. This distance is not less than one. It is less than one every time we measure the distance. We have to, this is a dynamic situation. This is a dynamic variable. This is a constant. This A, the limits value doesn't change. The value of this, these are terms AN. So we take 15 minus, let's say if our A was 20, 15 minus A. Oh yeah, it's 1. Let's just pretend. We take 18, 18 minus 15. Oh, it's 3. Yeah, that's less than 1. That kind of thing. When we replace this with 1, what we in our head we are doing is infinite numbers of distance measuring between each AN and that singular constant limit. That's the math that's happening. Do you get?
Don't quite get it back. It might extend it a little bit. So wait,
Yeah.
we can replace it with one. In like this.
No. A is no this guy? No, this whole distance, yes.
As one, even though it's less than.
No, it is. We replace it. This whole thing becomes 1, but here we will have the less. That's why I have to. Let me just erase this because I can draw this real fast. Okay. All right. We have. Okay. There are 2 things that are going on. I am talking about something else, and you are confused about something else. So
So I might be confused about
this whole thing is 1.
Even though from our antecedent, it says that it's less than algebraically, even though it's not equal to, it's not anything like that, we can just replace it with 1.
No, we do this.
So we have to have a.
We have to have this sign there.
Okay.
This whole thing. Okay. What's happening is actually if you write it on this side, it'll make more sense. Yeah, no. This is very good because this is going on the internet. So, because I haven't cussed yet, this whole term is less than 1 plus epsilon. Let's meditate on that. Is that true? This whole term,
yeah.
Because this number that you get is always less than 1. So this number is going to be less than, so this is less than 1 plus A, which is a constant, unchanging. This thing is then always smaller than what came before it. We don't replace this thing with 1. We replace this whole equation with this formulation with the less than.
Oh.
Okay.
Now it clicked.
Okay.
So then.
Because I've been talking about it wrong too. So that's, yeah, go ahead. Yeah.
So then A of N, it's our regular, our initial point. No.
This guy. This guy is all the clustering terms.
Is going to always be less than 1 plus absolute value of not equal to, not anything like that.
Wait a second. Oh, hey. So yeah, this term is not a single term. This
No,
is
it's dynamic.
no, yeah, it's a dynamic term that I'm using. So this is all terms an will always be less than this number.
Yeah.
There is nothing dynamic about that anymore.
No, yeah.
So this is, so we can then rewrite this whole math we just did. Very good. We're getting, this is really very, very good. This is then this, and this is the result of our math we just did. So what this is saying now is that the clustering terms, all of them are smaller than this number. There is a number that is bigger than that, and that number is also, is it in the, I'm thinking about the upper bound. Is the upper bound in the sequence? Potentially not. Remember, if in a set, 1, 2, 3,
Crazy on the
the 3 is the LUB, the least upper bound, and 5 is an upper bound. So is 7. So this is potentially not in the sequence, but it could be on, it is on the number line to the right of where the infinitely many have gathered that are part of the sequence. So those, and then what we're going to do is the whole sequence, including the infinitely many, are smaller than this number always.
So
Yeah. So yes.
we're moving on to the upper bound now.
Yes.
What
We all right now all we've shown is that the clustering clustering, because we're still under this guy here. The clustering members of the sequence are
always less than.
always less than.
Never be.
No,
Right.
because that's the upper bound. Okay, so now let's redraw the picture up here, and then we can, now the set comes in, because we have to actually do there's a phrase here.
Max set.
Yeah, the max function we have to use, and we have to look at the first n terms, and via inspection find it easily, we find it easily bounded by inspection. Okay, so why is it easily? Because it's finitely many terms. So let me draw the picture here. So I'm going to take this off because we are now pretty confident what these guys mean. So as you can see, the reason why math is difficult is that it's just very exacting and rigorous. And if you get just thinking about it incorrectly, it has happened to me so many times while I've been doing this with you guys. And that happens at home, where I didn't understand why the set comes in. And in this lemma, it was fine. In another proof, it was a total disaster. After that, I was like, why is, in my head, I said epsilon can be equal to 0, when it's always a positive number. When I put epsilon equals 0 in my head, the rest of the proof did not make any sense.
I went to like online, like
Yeah.
real analysis,
Hmm.
right?
Mhm.
Or, highlight, right? Now we learned, let's test it out.
Yeah, this is the best. This is the text you'd need to buy. It's for $15. And I gave him a PDF, and if you have your computer, I can give it to you. So yeah, and it's in this thing. Belding, look for Belding. And eat, guys, yeah.
I
Okay.
actually downloaded the whole thing now my OneDrive. It's fucked. So now I gotta wait. Oh, I saw physics C's. I just said download. Physics C, your daughter and yeah.
Yeah.
Now I gotta bleed.
Don't put stuff on just put it on your hard drive. That's what I would do, because it's, it's from the Russians.
I'm terrible.
Okay, so the first n, so now the proof continues. The first
Oh, true.
n, proof is continuing, sorry. So this is our line number, what's our line? L3. Really? You just do 2 lines? Where is,
Line 3, and then line 4.
oh, okay. No, these are the lines from the textbook.
Oh.
Yeah, so,
Yeah, one was supposed that limit.
Yeah.
A,
yeah.
and-
Okay, I'll go with L3. So the first n terms of the first term, n terms of the sequence, and I'm going to go over that in a second, are easily bounded by inspection. By inspection, he means using the max function. By easily bounded as in has an upper bound. Easily because we are looking at finite terms. First n terms. So we have, yeah, let me draw the picture first. So here we go. Uppercase N, and then our A is here, A ends, and then this is 1, and this is, okay. Hey, you can do that later. I mean, yeah, just stick it in there and then don't leave with it.
Oh, yeah, no.
Yeah, the keys, I'm just kidding. Okay, so this distance here is 1. Okay, so now he says the author of the book, Belding, the foundation, the authors say the first n terms, and let's say there's another one here too, A4. And so therefore this would be 5, right? First n terms, all the terms after which the terms of the sequence gather. So when I read this, I go, all the terms an after the threshold term. This is all the terms up to and including the threshold terms. So we are going to gather them into a set. So let's do that. And this is where the conversation gets a little, and we're going to discuss that in a second. There's a dot, 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 and in the dot, 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 you could get A4, A7, if this was a bigger number, let's say 10, 50, there would be like 43 in the dot, dot, and then we go A uppercase N, comma, and, oh yeah, I deleted the whole thing. So let me put this here. Yeah, I didn't stick the, what was that? 1 plus this thing. This is the result from the use. This is what we got after we used the triangle inequality. So you know what? From this, it seems like, remember that whole talk about that guy, the upper bound doesn't have to be a term in the sequence? The way this is laid out, it looks like it is. Okay. And so this guy falls right here. And so let's think about that, because again, as usual, even though I seem to understand this, there are moments of cloudiness. What this line is saying, and the set that the book creates, it adds this guy in there. It adds the upper bound. Because upper bound by definition is, so at, see, okay, the problem is the definition that I was using. Usually the upper bound is this, and in this book, upper bound definition is this. It can be the largest term, right? So anyways, and I'm going to double check that after we're done with this.
Just-
Yeah, go ahead.
Because by reading these proofs, right, every section, sometimes words like that. The first in term, I would assume that was like first term to the A to the N. Why did it imply that 1 plus absolute value of the A is in that term? Why? Because I would assume A of N would be the last term.
A plus absolute value. No,
A
this,
of N.
this, oh, okay,
I think that would be the last term.
okay.
First in term.
And that's where the problem is, because this guy, put this here. So let's discuss, this is the problem we have run into when your professor, that's me, is not a math PhD. So this is where it falls. You take that number and you add 1 to it. It's going to be sitting right here. Between the upper bound and this, there are infinitely many numbers. So why is the upper bound included in the terms of the sequence? That's the question we're trying to answer. And the upper bound in this case, which is, this will become M max. This is a term that is, it's supposed to be this, right? In this book. Let me just double check the damn book. This book is killing me. 4, okay, so 4, oh, we're right. 414, let me check the lemma. Okay. Not. No, it's good. Because this was something I was still kind of confused about. And here it is, 414. And somebody, don't get sad, math will make us very sad. And oh, you know what? It's me. That's what they do right at the end. So the definition I wrote was wrong. That really messed up. The bounded should have been.
Oh, okay.
Somebody shoot me. Because I just looked at the textbook has, and then in my, yeah, in here, you guys can look at it. I have it correct. That was just, there is less than or equal to. But when I showed the bounded, I used the wrong. Which means M is potentially equals. And in this case, it does. So therefore, we can stick it in. These are all the terms that are before or after the epsilon distance of 1 from the limit. And so this is a term of the sequence, but these terms are the finitely many terms that are not within 1 dash distance or epsilon distance of A, where epsilon is 1. Okay, yes.
Well, previous beforehand, but that is a term after A of N.
Say that again? Sorry, I wasn't listening.
1 plus after value of A, that term.
Mm-hmm.
Oh, yeah, term. It's not equal to A of N, but greater than A of N.
This is a term which is bigger than any term in here. This number is bigger than any real number inside here. But it is part of the sequence because there was an equal to sign here, which I did not put in when I was at this beginning.
So just on our picture, because
Yeah. Yeah,
sorry,
yeah.
right where A of N, where's A of N?
This guy?
Yes.
Yes.
Okay, that's A of N.
A of uppercase N, yes.
So shouldn't every point after A of N be in the threshold? Every term of N.
Oh, that's your question. Okay. Look at this straggler here. In other words, what's happened is, okay, that's a good question. So what's happened is this A, let's say, I'm going to put another term here. That's a very good question, and I have a very good answer for that. Thank God. My marker is going bad. Very good question. So what's happening here is, I'm going to put here A4. And the A4 is going to go here. Actually, A4 can go here, sorry. And then a comma. So you get, you go A1, A2, remember this was 5, right? You go A1, A2, A3, A4, threshold term. Now all the terms are going to be within epsilon distance of A.
Instantly.
And then there was a term that we didn't know that we created. That's this guy. We constructed this guy. And this term is also bigger than that. That's why it's at the end of this set. Even though a set, yeah, go ahead.
Or set, okay.
A set is not an ordered thing. But when we lay out a set, especially if it's finite, we order the things. Even though a set is a bag of, it's a collection of things, it's a bag of things.
So when we.
It's an unordered object.
Okay, but my question.
Yeah.
So sets.
Yeah.
When we write them in increasing order, do we write them in increasing order of
The
or the value of?
the value. What do we have here? We don't have one. We have this whole thing.
So not the value, not the subscript in, right? We're not labeling them, no. But okay, that's why.
This doesn't have a subscript, but it's a term.
It's true, but the value of that term. Okay, I got it now. So.
And so this guy here, value-wise, is bigger than the AN, but and the index number N is actually 5. Okay, index number 4, yeah.
You cleared it all up.
Okay.
There.
And I'm there too. I'm just worried about this video because I didn't put this. I guess we could leave it like that. I could put in, the.
Yeah, well,
yeah. When that shows up, it will stay there like that, like in white at the bottom. Because this was going really well. The questions were really good. So this is like very thorough. And therefore, now we can say, now we use the max function. M has got that. And we are now ready to declare. So we will just now declare. We're not going back to the inequality property, triangle inequality property. We are ready to declare our result. And the result is line 4. That we have now officially all the terms of the sequence are less than or equal to this M here. And we are done. For all N. This for all N means when we read this, it goes terms AN for all N. That this phrase makes this not a single valued variable, but a dynamic variable, which takes one value at a time, infinite times.
Okay,
and infinite times it takes a natural number and spits out a real number that is always less than 1 plus absolute value of A? Yes? Okay, last question, yes. Because I have to let Liliana go, yes. Good,
I thought,
yeah,
okay, so
yeah.
I'm gonna say the AN that equals or is less than
The small an, which one? This one, right here, my finger.
that one.
This guy,
Yes.
this is at this point, these are just the clustering terms.
Yeah, these are all so those.
When we generated the, we made sure that we generated something that was that was randomly on the right hand side, because all we had to go was this. We had to use the conditions of the convergence sequence. It's a very good question, actually. We had to use the conditions of the convergence sequence in order to generate an upper bound, which is part of the sequence. And then from there, we try to generalize it because it's outside of the convergence sequence. That's when the set comes in. And we take the finite many before and after the convergence sequence condition, which is sitting here. This part here is the convergence sequence. So you could even write that down. That's, again, excellent questions today. This bit here is the convergent sequence business. This here is where the stuff that goes into the set. And once we do that, we can then do that without the n is greater than n condition, because this is under the tyranny of, sorry, this thing is under the tyranny of that. So it's not useful. This is a very different statement from that, because here an is all terms, here an is only the clustering terms.
Okay.
So this step of using the max function and the sets generalizes our case, because we were stuck with this.
So for that whole set, sorry.
Yeah, go ahead. No, it's fine. Yeah.
So for that set that has all the cluster terms inside of it.
No, this set does not have. This is a finite set. This set is a finite set.
Okay.
I thought about that. So it's a very good question. It is a finite set that only contains the stragglers before and after the patch where there are infinitely many terms. That's why it is easily inspected to be bounded. What is easily, the first n terms of the sequence are easily bounded by inspection. What we find is, we find that these terms are bounded by this, and then we generalize to this. All we're doing here is finding the upper bound for the finite many, and then saying, in fact, the upper bound for the finite many is also the upper bound for the infinite many, which is still a weird jump, but I think, what do you think, Chris? Is this legit? There's something that I don't know. There is a conceptual jump here.
What did we even use the A of n is less than 1 plus A?
Oh, that's M. It's this. It's this guy. This guy is this. The value of this is actually, oh, sorry. This thing is actually equal to, this one's a bad one. This thing is equal to 1 plus an. So that is fine. The question is, can we say that this is an upper bound for everything in the sequence? Because, and I think there's something that I don't understand yet that's missing. Or my question is just wrong because I don't understand something. Yes.
Maybe the set we're looking at down there is the part of that sequence, but as a whole, the whole sequence is in fact bounded by that.
Oh, okay. I see. If oh, now I understand why this works. If the upper bound 1 plus absolute value of A is bigger than all the straggling finite many, and they're also on the right-hand side. See, it is bigger than A4. A4 is bigger than anything here because the position of the real number on the number line gives its size.
Yeah.
Right? The further right you go, the bigger the real number is. But the natural numbers can go back and forth because, right? So yes, it makes complete entire sense. If we say, when we make the statement that the upper bound for the finitely many is this number, it is automatically bigger than in the infinite set of numbers. And we don't want to put infinite numbers because we want to do it by inspection. But putting a finite number of things in a set and saying which one is the largest. Yeah, or you can use a computer. This can all get coded and which some idiot will do. All right, Liliana, you're free to go and I'll be emailing you the assignment.
So sorry, Liliana.
If you're still there, or if you're not, where is she? I'll text her because she's probably doing the chat thing. So Liliana is all set. No, she's our oh yeah, I think she has now, thank you. She just said thank you. Oh, and I'm gonna say, have a great day, Liliana. She's one of my best students ever. She really is. Have a great day. Now, let's continue with the questions. Jake is still there. Good.
I'm here, yes.
The lower bound, I'm gonna say A1 is up there.
Okay, so this whole, no, here. Okay, here's the, so the definition of a sequence or convergence sequence is done. Okay, convergence sequence says that as we are going towards the right, there's going to be a point where all the terms will start clustering around one of the terms of the sequence, which we're calling A. Sorry. Yeah, that's what I did last time too. I ate one of these things without the cheese. So I'll do the whole thing.
Cheese.
Cheese.
You can
Sorry.
eat cold pepperoni pizza and not get sick, but each time I eat cold cheese pizza.
You get sick?
Oh yeah, it's not something about my stomach.
Oh, it needs warmness. Look at the amount of cheese. Bastard. Okay. Excuse me. So now we're done with the proof officially. So this is just for illustration. So what if your sequence was A1, A2, so decreasing, right? AN, and then here we have epsilon. Then this would be plus, and this would still be minus. And then they all fall here. And one guy is here, A3. So then we will be constructing a lower bound. And our lower bound will sit right after this. Because we'll take this to be 1. This is our lower bound. So a sequence that goes towards the left will then have not an upper bound or lower bound. It will have a limit. It's, yeah. And these numbers could be negative numbers, right? And if they are,
The terms negative? Or
yeah, the real numbers will be negative.
the real number.
The indices will always be positive numbers, always natural numbers.
Oh, yeah.
So
Real.
are we doing real analysis today?
No.
Not natural analysis. I feel good. I think it was a while. Oh,